Hey, Allie.
Hi guys.
So you said 8.2, number 14?
Mm-hmm.
Okay. Santa Claus has 5 toy airplanes of each of N plane models. How many ways are there to put one airplane in each of R identical stockings such that all models of planes are used? And R is equal to or greater than N, apparently, yeah? Okay. So what are you guys thinking?
We just really weren't sure how to, I guess, start this one, especially not knowing like how big R was in comparison to N. Like, are we going to run out of airplanes at some point? It just weren't really sure how to start there, I guess.
Well, so the point here is they have a total of 5 N planes, right?
Mm-hmm.
There's 5 each of each one of these plane models. Okay. So yeah, I guess they could run out of plane models, right? I think that's why you need to use inclusion exclusion. If there was no restrictions at all, you could probably just straight up use some kind of, selection with repetitions, paradigm or something. So let's think about this. So you have 5 each of these N plane models. You have R identical stockings. Okay, and what are you going to do? All right, I see, okay. So, so what do you think? Any ideas?
I mean, if we were going to do it in some sort of inclusion exclusion way, it seems like we could define sets like A sub 1 is the set where like no child gets one of plane model 1 and so on, and then do an intersection, like a intersection of complements type problem. Yeah.
Okay. Man. I liked the way they set this problem up because it makes you try to do one thing because of the problem context, but the reality is you should kind of be thinking in the other direction. Okay, so this is like a balls and boxes type problem, okay? But what do you think the balls and what do you think the boxes are?
The stockings are like the balls and the airplanes are like the boxes.
Yes. The stockings are the balls, and I think that's why, if they were really wicked, they would have actually not used the letter R or something like that for the stockings themselves. Okay, but so what Ilona is saying is that the boxes are the plane models. So there are N plane models, yes? And then what you're doing is you're just throwing these R stockings into these plane model boxes, okay? So if like okay. So if 5 of those stockings fell into box number 1, what would that mean?
It means that airplane model number 1 is in 5 stockings.
Yeah, right. Because we already knew that each stocking was going to get exactly 1 plane anyways, right? So it falling into box number 1 just tells us to put plane model number 1 into that stocking, yes? So, okay, translate the problem then. What are we saying about these boxes? The boxes are the plane models, right?
Mm-hmm. Yeah.
So they can have at most 5 balls in each box.
Yes.
But according to the restriction of this problem, at least one,
Uh,
right?
does it say at least one?
Well, all models of
Oh,
planes
all
must be
models are
used.
used. Yeah, but that's kind of easy to take care of, isn't it?
Mhm.
Because all you do at the beginning is you just straight up put a stocking in each box. Does that make sense?
Mhm.
And so you're going to have R minus N stockings left to distribute. And that's why R had to be equal to or greater than N, right?
Mm-hmm.
R minus N things left to distribute with what restriction? And now the restriction kind of changes just slightly, doesn't it? Because if you
At
put
most 4 in each.
if you put 1 in each box to begin with, then you've used up one of your 5 plane models of each one. Does that make sense? So then you just distribute the R minus N stockings into those N boxes in such a way that you don't distribute any more than 4 in any given box. Yep.
Okay.
So how would you define your sets? What do you think would be a good way to define your sets? What do you think A1 should be?
Would you do that where model 1 is, or wait a second.
Yeah, I like how that was starting.
Yeah, I had it, and then I think it got mixed up in my head.
Okay.
Where model 1 is in 4 or more stockings.
Yes. Well, 5 or more.
Oh, yeah.
So we made sure that there was already 1 in there, and we take the R minus N remaining stockings and start throwing them in the boxes, which are the plane models. And so A1 is going to be those distributions that have 5 or more in box 1. Yeah. Because that would guarantee that you actually used how many of plane model 1 at least?
You've used it at least once, and well, you've used it more than the allowable.
Yeah, you've used it at least 6 times actually. Does that make sense?
Yeah.
Right. So yeah, is that helpful?
Mm-hmm.
All you have to do is just take I guess you're going to want to do the intersection of the complements of those things. And it's not, I mean, you're going to, I think, yeah, I think that's going to be right. Yeah. I mean, you're going to keep like subtracting away, you know, like 5 at a time from R minus N or something like that. You're going to keep subtracting away 5 at a time from R minus N as you move down the line in the formula for inclusion exclusion. But I think that's definitely doable. So you're going to have like N sets, right?
Mm-hmm.
And A sub general is going to be that 5 or more from the R minus N fall into box I. which would guarantee that 6 or more planes of model I were used, which is not good. Okay, so you don't want that to happen. Yeah.
Man, that's trippy.
I liked how they kind of try to suck you in because you feel like you want to throw the planes in there, right?
Yeah.
Don't you want to throw the planes in there? And you want the boxes to be the stockings because, I mean, obviously planes fall into stockings.
Yes.
but that's not what you do. And that's why they used R and N. When I first read it, I was like, R? What in the world? And then I went, oh, okay. I see how this is going to work. Okay. Yeah, that was devious. Okay. What else? What other questions do you have?
Can we talk about problem 18?
Okay.
I wasn't quite sure with this one just because, I mean, and we must not have to know this, but it seems like we should have to know how many numbers we have to know how many are odd and how many are even. And it was just, that was tripping me out.
Okay. Yeah. So yeah, I mean, there's probably going to be 2 formulas, one for the case where N is even, I guess, right?
Mhm,
And one where N is odd or something.
mhm.
So how are you going to set it? Okay, so, all right. So what are you going to do? How would you set that up?
Well, so my gut instinct is to, I mean, kind of define N as like 2K plus 1 or 2K, depending on if it's, odd or even. And then to kind of, then we know, okay, we have like, in the even case, we have K odd and K even and go from there. But I don't really know if that's the right way to start.
Yeah, but we could, we could, I mean, we'll deal with that later. Like
Okay.
how, I mean, so I just want to talk about the problem more generally. I mean, so for instance, let's just think about the beginning of the permutation.
Mhm.
Okay. Is it okay to have 2 in position 2?
Yeah.
Sure. But can I have 1 in position 1?
No.
No. So let's just think about the front end of the permutation. We'll worry about the back end later, okay?
Okay.
Worry about the front end of the permutation. So you can't have 1 in position 1. You can't have 3 in position 3. You know that you can't have 5 in position 5. I'm just thinking about the front end of the thing. I mean, N, even, or odd, we'll kind of deal with that later on. But would you define your sets through which you will apply inclusion exclusion?
Would A sub 1 be the situations in which 1 is still in its own position?
Yeah, where 1 is actually in position 1. Yes, yes, yes. And just because we don't want to get confused, let's like not say A2, but A3.
3.
Okay, what's A3 going to be?
3 is in position 3.
3 is in position 3. Those are very easy to count. Know what I mean? Because all you do is you say, well, A1, I mean, just put 1 in position 1 and then just go wild with the rest of it. So it'd be like N minus 1 factorial, essentially.
Yeah.
A3,
And they're all going to be that, aren't they?
yeah, they're all going to be just N minus 1 factorial, right, for the singular sets. But then it's also easy to count the intersections, isn't it?
Mm-hmm.
So like A1 and A3. I mean, that's just, you put 1 in position 1 and 3 in position 3 and then just go wild with the rest of it. Yeah. So it's going to be n-2 factorial. You see how this is going to work?
Mhm.
What am I'm going to want to compute the size of the intersection of the complements of those things, right?
Mhm.
Whole number is in factorial, and then I subtract off, and maybe we'll have to think about fiddling with, you know, what's going on within exactly, but we at least know what the structure of the formula is going to look like. Yes. So the problem is basically solved at this point, and now all we have to do is kind of fiddle with n even or n odd. Yeah.
Okay.
So what would be the difference then, Katie? Now that we kind of see that, how would this change based upon n being even and n being odd?
Well, the number of like intersections is going to change. Like the number of two-way intersections, the number of single sets too, I suppose.
Yeah, right. Yeah, right. So yeah, that's essentially it. You just have to
Okay.
think about that, right?
Okay.
If I were you, I would play around. I mean, again, don't try to bite off more than you have to. This is what I do all the time. I just say, well, n equals 3 and n equals 4. What's the difference? And typically that's enough information for me to be able to say, oh, I see what's happening. And then I can just define what's happening for n even and n odd. So trying to like do the general case too quickly sometimes creates more confusion than it deserves. So just look at the case 3 and 4 and say, oh, I see what's going on, and then deal with it accordingly. Yeah. Believe me, I've done that plenty of times where I've been working with n and then I've gone, man, I don't know what I'm doing. And then I do like n equal to 5 and I say, oh man, now I suddenly know everything about this. Why didn't I do that 2 hours ago? Come on, right? So, yeah. Okay. What else? Other questions?
I have a question of trying to like visualize what's going on in problem 16, where we're coming up with different codes. Because when I think of this, I kind of think of kind of like a permutation, like doing different slots. So like say we have A, B, C, D, like going all the way across, and then assigning them to new letter values underneath. But then when I think about it that way, I just think it would be like 26 factorial or like the different
No.
way. So I don't know.
Do you
Yeah.
see the connection to do you okay. Do you see the connection to derangements? So like you're thinking about it in 2-line array notation basically,
Mhm.
right? Where you have
Yeah.
A, B, C, D, blah, 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 Z, right?
Yeah.
So A, B, C, D all the way to Z. And
Mhm.
then below it, what do you not want to see connected to A?
Oh, so it is like a derate. You don't want to see A.
You don't want to see A.
Okay, that makes sense. I
Yep,
was thinking it was saying like the codes all have to be like totally different from each other or something. But
No, it just has to be a derangement of the 26 letters.
okay.
To be deranged. You don't want B corresponding to B.
Okay.
Therefore, it's just a derangement of order 26.
Okay. Gotcha. That makes sense.
Yeah, and you know derangements are connected to the constant E, right? I mean, basically, the number of derangements of order n is very sharply approximated by n factorial over E. That was kind of the interesting. And what's weird to me, and I still don't, I mean, I almost don't believe this, but it's true. So suppose that 10 of us were in the same room together, which is an unlikely event nowadays, right? And suppose that we all had different, we all had our own hats, okay? And then suppose we all closed our eye, we got in a circle, and we all closed our eyes and threw them into a pile in the middle of our circle. And then we all kind of kept our eyes closed, reached down and grab a hat and put it on. What's roughly the probability that we're all going to get different hats from our own? Well, essentially 1 over E, okay? Which is like basically 36% or something, okay? Is that true? I just pulled that off the top of my head, but let's see. 1 divided by E. Where's E on this calculator? What? Where is E? Is E even on here? I see pi.
How can it call itself a calculator?
Oh, here's E. Oh yeah, it is. It's 30. It's basically 36. Wow, 36.779%. Okay.
Not too shabby.
So 1 over E is basically like 37%. Okay, so if we did that, the probability that we would all get different hats, that's like a derangement, would be essentially 37%. Now, suppose that 10 million of us made a giant circle, okay, and we all threw our hats in the middle, okay, and we blindly reached in and pulled out and put on a hat. What is the probability? What is the probability that we will all get a different hat from our own? The same as the case of 10. How is that possible? Does that make sense? They're both basically 37%. That just seems ridiculous, but it's actually true. Seems like it should be way less likely in the case of 10 million people as it is of 10 people. But it turns out it's not that different. It's basically the same. I don't know. Does that surprise you? I mean, that definitely surprises me, but it's true.
That's interesting to imagine.
Yeah. Yeah. I think people should be more shocked by that. Okay. All right. What other, okay, other questions?
I was wondering about 10B. A and C I was comfortable with, but B with the negative, it just kind of threw me off. So I wondered if we could talk about that.
One of Katie or Elise asked me about that. Who asked me about that? Was that?
I did.
Okay, so what did I say, Katie? What do you do?
So you said we could just define like y to be x plus 10. So basically we just add 10 to each of the x's, and then you have to add 40 to the other side of the equation.
Yeah.
And then it simplifies down nicely.
You see what I'm saying, Ellie? So if you add 10 to each of the variables, which amounts to
That makes
adding
sense.
40 to the right-hand side, you get some new variables like yi. So yi is basically xi plus 10, okay?
Yeah.
And so you get new variables yi such that y1 plus y2 plus y3 plus y4 equals 68, yeah?
Okay.
But what are the ranges of those variables y? What about?
They'll be able to go from 0 to 30.
They'll be from 0 to 30. Exactly right. Exactly.
Okay.
That makes sense.
Yeah, thank you. Was that in a video that I missed? Or
You know what? I've been kind of screwing that up sometimes where I like forget to start recording. Maybe it's in a video somewhere. I'm not sure. But if no one marked it or marked the timestamp in the document, that might have been one that I forgot to mark. But it's in here now. You're on you're on candid camera. So okay, what else? What other questions do you have?
So you briefly mentioned this in the lecture, but I just want to make sure I was following. So when we were going back to our original example right at the end of the lecture and applying the formulas we found,
Mm-hmm.
you had in parentheses like the different pies or whatever, but that was just to reference them. Like that wasn't any sort of
Yeah.
multiplication or anything, right?
Yeah, those didn't have any
Okay.
mathematical meaning
Okay.
other than the that number is coming from those two permutations.
Okay.
I think I'm going to change that in the notes because I was even confusing my own self when I was reading through that. But yeah, that's those didn't have any meaning. Okay.
Okay.
I tried to kind of put a brace above them and say this is coming from C1 or
Mhm.
something. Yeah.
Okay.
And that Burnside's theorem is something spectacular. Every time I think about it, I just think, man, that is just amazing. And it all is just comes from this simple idea of the fact that the same number of permutations that fix a coloring in an equivalence class is the same as the number that move it anywhere else in the equivalence class is the same as the number that fix any of those other ones. And therefore, there's this careful counting of the number of elements in the group going on. And so everything just falls out of that. Yeah. Man, I couldn't believe that when I started compiling that lecture, and then I was like, man, why is this taking so long? Then I realized it was like almost a 100-minute lecture. So sorry about that. I didn't know that had happened until I was done. I should be keeping closer track of time as I'm doing that, but I don't know. It also didn't really make a whole lot of sense for me to stop and not just finish the thing. But you know, I wouldn't have been able to do that in class, I guess, either. So I wouldn't have been able to keep going like that. So I do apologize that was so lengthy. Wasn't that exciting though? Come on, you gotta admit, that's pretty exciting. Did it make sense? Hopefully. Yeah? Okay.
Yeah.
Okay. All right. And like I said, the rest of chapter 9 is going to be devoted to using Burnside's theorem to our advantage, trying to come up with clever ways of counting the number of colorings that a permutation fixes, because that's what you really need to know. And also, eventually at the very end of the chapter, we'll have a pattern inventory. We'll be able to go back and use generating functions in conjunction with Burnside's theorem to deliver a pattern inventory for these colorings. So I'll be able to say not only how many colorings there are that are truly distinguishable under the symmetries of the group, but also how many of them have like 2 black and 2 white, for instance. Does that make sense? Or how many have 3 yellow, 2 green, and 1 red, okay? And that's amazing. That's amazing that we're going to be able to do all of that. So we'll be able to give a pattern inventory, a complete pattern inventory. All right. What else? Other questions?
I have a really stupid one on
okay.
number 1.
Oh,
I don't know why, but I'm having trouble seeing how this connects to the inclusion exclusion, because the way that I was thinking about it was kind of more direct, where you just make sure you include 1, 2, and 3 in the sequence, and then you order those 3 things, and then you can select any of the remaining n-3 digits from the 10 available options. Am I like missing?
well, you can definitely do it that way, but the issue is you're going to have to be very careful, because when you place a 1 or 2 and a 3 in there, you may accidentally like double, triple, whatever count situations where they happen to appear elsewhere. Does that make sense?
Oh, yeah.
Okay. So you would have to split it up into a massive number of cases
Yeah.
where you say there's exactly one of each. There's exactly 1 1 and 2 2s and 1 3. There's exactly, so you would have a massive sum.
Yeah.
Whereas the way that you can do this using inclusion exclusion is how. So someone want to, you know, speak into that void?
So you could let A sub 1 be the situation in which 1 does not appear in the sequence.
Yeah. A sub 1 is the number of M-long sequences that do not contain a 1. All that does is it basically just eliminates 1 from your consideration. All the others are fair game. Similarly for A2 and A3, and you're just going to compute the size of the intersection of the complements of those sets. Yeah? And then
Yeah, gotcha.
exclusion just goes whoop, and
Yeah.
solves the whole thing, right?
Yeah, that makes a lot of sense. I don't know why. For some
Yeah.
reason, when I looked at it, I'm like, why am I not seeing the connection? So, okay, that makes sense.
All right. Yeah, good. Good, good. Yeah. Right. I was going to ask you guys. So, in this last lecture, I did a few things where I was actually writing on. I kind of logged myself into the Zoom meeting on my iPad, and I actually gave my own self the permission to write or to annotate on the actual shared screen itself. Did that show up all right? I mean, I
Yeah.
watched a little bit of it, and it seemed
worked
like it was
well.
all right.
No, that was really good.
Okay. But one thing I was noticing is that sometimes it's like I would write something and then it would go boom and just kind of appear. But I guess that doesn't really
Yeah.
matter that much.
It worked.
Yeah. Anything else? Well, hey, thanks for stopping in. Thanks for your good questions. I'm gonna I'll try to go into this video and timestamp some things, and I'll update that list that Aaron has been tracking. But I'm, you might want to check me to make sure I don't miss something or something. Okay. All right. All right.
Thanks.
Thank you, Dr. Hammett.
Thank you, Dr.
Yeah. No problem. See you guys later.
See ya.